All right, here are light notes part 2. In opaque materials, any coordinated vibration given by light to the atoms and molecules are turned into random kinetic energy. Kinetic, it's moving. This is into internal energy, so it's internal, inside. Since in the last set of notes we were talking about transparent materials, now we're going to talk about opaque materials. Materials that absorb light without re-emission and thus allow no light through them are called opaque. Wood, stone, and people are opaque. In opaque material, any vibration from light are turned into kinetic energy, that is, into internal energy. The materials become slightly warmer because instead of re-emitting the light is held in, so it warms up the object. Metals are also opaque. In metals, the outer electrons of atoms are not bound to any particular atom. When light shines on metal and sets these free electrons into vibration, their energy does not spring from atom to atom. It is re-emitted as visible light. This re-emitted light is seen as a reflection. That's why metals are shiny. Our atmosphere is transparent to visible light and some infrared, but almost opaque to high frequencies, like ultraviolet waves. The ultraviolet that gets through is responsible for sunburns. Clouds are semi-transparent to ultraviolet, so you can get a sunburn on a cloudy day. Ultraviolet also reflects from sand and water, so you can sometimes get a sunburn while in the shade or under a beach umbrella. Why is glass transparent to visible light but opaque to ultraviolet light? The natural frequency of vibration for electrons in a glass matches the frequency of the ultraviolet light, so resonance in the glass occurs when ultraviolet waves shine on it. These vibrations generate heat inside of a wave re-emission, so the glass is opaque to ultraviolet. In the range of visible light, the forced vibrations of electrons in the glass result in re-emission of the light, so the glass is transparent. Lower frequency infrared causes entire atomic structures to resonate, so heat is generated, and then the glass is opaque. Why does light not pass through opaque materials? When the light shines on an object, some of the rays may be stopped while other rays pass right straight through it. Shadows. A thin beam of light is often called a ray. It's important to know. Any beam of light, no matter how wide, can be thought of as made of a bundle of rays. A shadow is formed when light rays cannot reach it. Sharp shadows are produced by small light sources nearby or by large sources that are farther away. However, most shadows are somewhat blurry, with a dark part on the inside and a light part around the edges. A total shadow is called an umbra. A partial shadow is called a penumbra. A penumbra appears when some of the light is knocked but other light fills in. That's why whenever you have several light sources, like if you look at our room, you won't see our shadows anywhere, like on the ground or on a table or anything, because there's other light sources able to fill in. When there's one light source in a room, usually you will get a shadow that way. But you see that it's called an umbra. This is where we get the term umbrella, because it covers. A large light source produces a softer shadow than a small light source. Here we go. An object held close to a wall casts a sharp shadow. As the object is moved further away, penumbras are formed and cut down in the amount of shadow. As you see, this one's much sharper than this one as it gets further away, because light is able to get around it and you don't get as good a shadow. Even further still, the further away, the blurrier the shadow. More of a penumbra. A penumbra occurs when the moon passes between Earth and the sun during a solar eclipse. The moon's shadow barely reaches Earth. If you stand in the umbra shadow, you experience brief darkness during the day. If you stand in the penumbra, you experience a partial eclipse. The sunlight is dimmed and the sun appears as a crest. Earth, like most objects in sunlight, casts a shadow. This shadow extends into space, and sometimes the moon passes into it. When this happens, we have a lunar eclipse. A lunar eclipse can be seen by all observers of the nighttime half of the Earth. Shadows occur when light is bent in passing through a transparent material such as water. Light travels at slightly different speeds in warm and in cold water. The change in speed casts light to bend, just as layers of warm and cool air in the night sky bend starlight and cause twinkling. Some light gets deflected a bit and leaves darker places on the wall. The shapes of the shadows depend on how the light is bent. A heater at the tip of this submerged J-tube produces convex currents in the water. They are revealed by shadows cast by the light as is deflected differently by the water of different temperatures. Why are lunar eclipses more commonly seen than solar eclipses? There are usually 2 of each every year. However, the shadow of the moon on the Earth is very small compared to the shadow of the Earth on the moon. Only a relatively few people are in the shadow of the moon, the solar eclipse, while everybody who views the nighttime sky can see the shadow of the Earth on the moon, the lunar eclipse. What causes the formation of shadows? Light that reflects at glancing angles from non-metallic surfaces such as glass, water, or roads vibrates mainly in the plane of the reflecting surface. Light travels in waves. The fact that the waves are transverse and not longitudinal is demonstrated by the phenomenon known as polarization. If you shake the end of a horizontal rope, a transverse wave travels along the rope. The vibrations are back and forth in one dimension. The wave is said to be polarized. Remember, this was our transverse wave as it went through here. Remember, it had right angles there, and there, and there, saying it's polarized. If the rope is shaken up and down, a vertically polarized wave is produced. The wave traveling along the rope are confined to a vertical plane, so it's going up and down these directions. If the rope is shaken side to side, it's horizontally polarized. So this one now is polarized like this to where this one is up and down. You have 2 different planes of vibrations going on, one vertical plane and one horizontal plane. A vibrating electron emits a polarized electromagnetic wave. A vertically vibrating electron vibrates a vertically polarized wave. So if you look at this, it's going to be vertically vibrating. And then if you have a horizontally vibrating electron, it emits a horizontal wave. So you have 2 electrons, one's vibrating vertically and one is vibrating horizontally. An incandescent or fluorescent lamp, a candle flame, or even the sun emits light that is not polarized. The electrons that produce the light vibrate in random directions. Instead of being vertical and horizontal, they go all different ways. If the polarized light, when the light shines on a polarized filter, the light that is transmitted is then polarized. The filter is said to have a polarization axis that is in the direction of the vibrations of the polarized light wave. Light passes through 2 polarizing filters when the polarization axes are aligned, but not when they are crossed at right angles. Here's some examples to think of what this is. So here's a rope analogy that illustrates the effects of the crossed sheets of polarized materials. So you see all the stuff that they have here that's working through here. You have the non-polarized light vibrating in all directions. Then you have a horizontal and vertical component. So one's going up and down and one's going left and right there. Vertical component passes through the first polarizer and the second. So I have this polarizer and it's letting just the light that's going vertical up and down through. And then this other one over here, again, it's going every way. It's going both ways here. Here the vertical component does not pass through the second polarizer because this polarizer is different from over here. This one is just vertical, lets vertical through. This one blocks horizontal, so it's not going to let any of those through. So it blocks both the horizontal there and it blocks the vertical here. So nothing is going to get through. Think of limousine tent. You can see out because of light sources outside of it, but you can't see in because it's blocking all the light. Here's a fence that basically is explaining the same thing. Both these panels are vertical, so it lets through the slits, it lets some of the light through. Here we have a vertical and then a horizontal. Well, it lets the vertical through here, but then it breaks off and doesn't let it through. Skipping flat stones across the surface of a pond, stones with flat sides parallel to the water bounce or reflect. Stones with flat sides at right angles to the surface penetrate the water or refract. Light behaves similarly. The flat side of a stone is like that of the plane of vibration of the polarized light. Light reflecting from non-metallic surfaces such as glass, water, or roads vibrate mainly in the plane of the reflecting surface. So glare from a horizontal surface is horizontally polarized. The axis of polarized sunglasses are vertical, so that glare from the horizontal surface is eliminated. So this is how your sunglasses work. They basically take and polarize the light one direction. Light is transmitted when the axes of the polarized filters are aligned. Light is absorbed when they are at right angles to one another. Surprisingly, when a third filter is sandwiched between the two crossed ones, light is transmitted. The explanation involves vectors, because as the vectors travel through, you get your vectors to add back up. Why is glare from a horizontal surface horizontally polarized? Alright, a pair of photographs or movie frames taken a short distance apart, about an average eye spacing, can be seen in 3D when the left eye sees only the left view and the right eye sees only the right view. Vision in 3 dimensions depends on both eyes giving impressions simultaneously from slightly different angles. The combination of views in the human brain system gives depth. A pair of photographs taken a short distance apart is seen in 3D when the left eye sees only the view from the left and the right eye sees only the right view. Slideshows or movies can project a pair of views through polarization filters onto a screen with their polarization axes at right angles to each other. The overlapping pictures look blurry to the naked eye. To see in 3D, the viewer wears polarizing eyeglasses with the lens's axes also at right angles. Each eye sees a separate picture. The brain interprets the two pictures as a single picture with a feeling of depth. A 3D slideshow uses polarizing filters. The left eye sees only polarized light from the left projector. The right eye sees only polarized light from the right projector. Depth is also seen in computer-generated stereograms. A computer-generated stereogram, slightly different patterns are hidden from a visual view. In your book, you can view them. We don't have this book, so I wouldn't worry about that. Which pair of glasses is best suited for automobile drivers? The polarization axes are shown by the straight lines. So you have ones going up and down, left and right, or one going up and down and one going left and right. Pair A is best suited for the vertical axes, block horizontal polarized light that composes much of the glare from horizontal surfaces. Pair C is suited for 3D glasses. So that's what 3D glasses look like. And then pair A, they're vertical. They let vertical light through, but they don't let horizontal light through. And most of the glare you get off of roads and stuff like that is horizontal. So that's what you want. Try these optical illusions. Are the vertical lines parallel? Do these lines move on you? What does this sign read? Did you catch yourself? Paris in the spring? Did you just say Paris in the spring? How can you see photographs or movies in 3D? All right, this is the end of the notes. That's all for light.